Hello, welcome again. And let's start. So you probably recall that we had some complete Heyting algebra H. Then I defined as our values. Then I defined H set as a pair of one usual set plus some function R. That R goes from A times A to H. You have to read RAB as somehow the value of equality between A and B. So that's just your primitive equality. And if you remember, we had these two things, that R is symmetric and R is what? Transitive, but not necessarily reflexive. Therefore, we defined E of A as RAA. How much, to some extent, to what extent A equals to A? That's the extent of which A exists, right? And then we also had maps between these guys to have a category. So if you have a R and BS as two H sets, H is always fixed. So by a map, simply you mean some sort of H relation, meaning that something that goes to that. So you have to read FAB as the value of the fact that A goes to B via F. And then you had to have some properties, right? That F is defined on the existing ones. F is total, F is functional, F is well defined, meaning that it respects equality, etc. And then we had identity, we had composition, and therefore we had this category of H sets. And so I claim that this guy, for any H, complete Heyting algebra, should be a topos. Therefore, I had to check three axioms that any topos has. And we started with finite limits. We checked that. You remember, for instance, the one that I need today is just a terminal object. The terminal would be just a singleton as the usual terminal in set. And here you define as constant 1. So star equals to star, really. And so we had finite limits that I don't recall. We had exponentiation, exponential objects that I don't recall, but that doesn't matter for now. And the last thing that we didn't check was sub-object classifier, right? That I have to start with now. So if you remember, sub-object classifier means that there is some guy such that it classifies all sub-objects, right? So sub-object means one monic. So therefore, it is kind of helpful if we know what is a monic in this situation. So of course, monic means simply if you have some AR, then monic means just monic map in terms of the category from BS, some BS to AR, right? But at least in set theory, we know that we can characterize any, and that's the source of having a sub-object classifier, right? That if you have any subset, yes, any sub-object is just a one-to-one map from some B to A. But at the same time, we can read them as, a map from A to 0, 1, right? Such that blah, blah, right? So the same kind of happens here. So there is a notion that's called H subset, because we read anything and we make it, relative to H. And H subset of what? Of AR. And the natural thing to do is what? Is that it should be some map, say some chi, such that it goes from A to H. That is the extent to which the guy is inside the subset, if you like. but it cannot be any function. It has the following properties. First, it respects equality, of course. So then if you have A and A primes A and chi of A, then it's less than chi of A prime, right? Simply, I'm saying that if you pick A and these two guys are equal, then you have to pick A prime. And also, your chi is on the existing objects, meaning that if you pick your A, then your A exists. Or if you like, E of A. So, right? These are my assumptions. And whatever whatever function that you have with these properties are called H subset of A. The good news is that there is one-to-one correspondence between sub-objects of this guy and let's say 1-to-1 correspondence between these and H subsets of AR. I won't prove it because it is just something tedious to check, right? But maybe that's good to see the maps between them, right? How to transform one to the other and back. So one is easy. So this one is easy, kind of. This. So let's say that I have a map for this part of the game. It doesn't matter to have just Monique. So you can have any map. And how to define one H subset? I have to go somehow reading F. I have to go from A to H. How to go it? And let's say that probably that's M, and this is chi of M, right? How to define chi of M? The usual set theoretical idea is what? Is that if you are in the image of B under M, then that's fine. Otherwise, it's not, right? So simply you are saying that the value is the value of existing something in B such that it maps it to our A. So meaning that A, the chi M of A, the value of A inside the subset is simply there exists B in B and such that you have M of B A, right? B goes to A. There exists some B that goes to A, the value of which is just the value that you want, right?
Sorry, this
Mm-hmm.
is it the name of the map or is it indicated something?
It's the name of the map.
So, but the map is mentioned.
And what is the definition of map? Map simply is just a map, a set, a function, sorry, from B times A to H.
But I think I'm forgetting. So sub-object is something with a map.
Yes. Yeah. In the definition, no. Just in the usual case, right? So even if you have a function in set theory from some B to A, you can define this subset simply by the subset is just the image of B, regardless of being Monique or not, right? The problem is in the bijection. So you can simply go from this part to that part, even from any map to AR, not just sub-objects, right? So
That well, that also include that B exists, right? Because that is always smaller than NB.
exactly. So as long as I assume this, then always it exists. So that would be maybe something reasonable to check that you have these two properties. The one that you mentioned is this one, right? So if I have chi of A, then I know that A exists simply because in each of these cases, for any B, this implies existence of A because that's a map. Therefore, A exists. But B, I don't care for now. And then also equality you can check, right, by definition. And maybe before going to explain the backward one, maybe I have to mention something, and that something is that, of course, if you, how to say it? What I want to say is that, okay, two things that I have to say. One, um, yes. So that is somehow the characteristic function of that M. Therefore, they had to have some relation with each other. But before that, let me say that this chi M that I defined, or any chi actually, any H subset, you can just change it somehow in presentation to really a map from your AR to H this. So you remember this guy, right? That this is just the H set of the values. You pick your H, and this is just the equivalence, the usual equivalence to Heyting arrows, right? What I'm saying is that these two guys actually are the same thing. So at least this way, you have to define, let's say that chi tilde is a map assigned to chi. And chi tilde, if it's a map, it should go from A times H to H, right? So you read what? You read some A, you read some H as the value, and then you have to compute what? Let me make it easy.
But to which extent the chi of A is equal to H, which should be chi of A being equivalent to H?
Yes. Maybe that's a good point to mention, that we had some way to construct functions like this, that if you have some AR and some BS, right? And also you have some function, real function from A to B, such that it respects the equality, meaning that if you have RA, say B, B is a bad name, so A1, A2, then it's less than SF, A1, F, A2, then you can define big F, right? Like simply as you said, right? So F should go from A times B to H, and so FAB means that A should go to B, and the definition simply is what? Is S of FA and B, the equality between them. But also we need something else, and that something else usually here is that A exists. Right? Because we assume that functions are on the existing things. And the same happens here, right? So that is, I guess, not enough. We cannot prove the existence of A from this. So I guess we have to assume. The existence of H is just, doesn't matter. So, but my point is that we have that function really, right? So we have this function A from A to H. We can use it to define chi tilde, but the point is that the map from A to H must respect equality, right? And respecting the equality here in this case would be simply if R A1, A2, then it is less than chi A1 is equivalent to chi A2, right? Because equality here is equivalent. And that is the case simply because I have it, right? I have A prime, chi A implies chi A prime, right? This guy. And from that, I have this less than chi A1 implies chi A2, and the other way around, right? So, okay. And okay, I explained this to say this, that if you go from some BS to AR, and if then I define my chi M of A as we did, like there exists B MBA, and you know that this chi M goes from A to H, and then you can define this tilde guy from AR to H this. Then what I want to say is that if you go from B to that one, it is just the trivial one. What I'm saying is this, that chi M tilde OM equals to constant one. And it should be, right? Because that's the characteristic of the guy. So if you compose it with the guy, then it should just answer one. Always, right?
You're doing the right-hand side of this board corresponding between sub-objects.
Yes.
Each subsets.
Yes.
So the thing on the bottom right is showing how you go from a sub-object to an H subset.
Yes.
So finish that, right?
No. So if you have M, then you define your chi of M like this.
Okay.
That's it.
Chi of M is the H subset.
Yes.
Okay. So what are you doing now?
Then what I'm saying is that, okay, now forget about this thing. And then what I want to emphasize is that whenever you have one H subset, you can also see it as a map from the H set AR to this H set. That's the explanation of that. Of the fact that you can define from any chi some chi field.
That's not the one you want yet, but it's other one. Because it will be a
No. We are still on this direction. Yeah, no. So this direction, so nothing about the backward direction, right? We have this direction and this is completed. But there are some remarks about this thing. The remark is that first you can change your chi to chi tilde as some proper map from your A to the values, let's say. And then the second thing is that if you compose this map, the characteristic chi n, lifted to H sets, right? Now I'm back in the picture. You start with M, you define your chi M. Chi M is a map from A to H. You pretend that it is actually a map from AR to H double arrow. And then what I'm saying is that if you compose it with M as two maps in H sets, it is trivial one.
So this picture is a lemma?
Kinda, yes. That I didn't prove. That's the yes, let's say lemma, if you like. We have this. You start with some M, you define your chi M, lift it to H subsets. Now you have two H set maps. You compose them, and then it says that it is just equal to one, the constant one all the time. Right?
So
Huh? So that's useful for later. So in the usual set theory, simply what I'm saying is this.
you're showing something about the structure of some category.
Yes.
But which category?
Category of H sets. The objects are H sets. The morphisms are the functions between H sets as I define.
But I think I've got it lost in start. So the sub-object, so the AR
Mm-hmm.
is a first class element of your category. But the H subsets is not in the category.
Exactly. They are simply functions from the set, the base set of the guy to H, of course, respecting something. No, but the map lives in sets really, not in H sets. This is just a P. Yes. So the whole point is that I cannot compose this guy with M, right? Because this lives in sets, the other lives in H sets. To compose them, I have to lift this guy to H sets and then compose. Hmm?
That behind someone. This is like I see what you're saying, but it's too abstract to mean anything.
Yeah, but okay, that doesn't really matter. So just believe me that this is the case. And to prove, probably you have to show that on any two things, right? And the guy goes from this to that. So then for any BH, that guy should be 1. And by definition, it is simply big join on A, in between, and then M, B, A, and phi M, say tilde of what? Of A, H, right? And this guy more or less is just simply chi M A is equivalent to H and E of A, right? Yeah. It is the proof of this equality. I'm computing this guy to show that it equals 1. Right? So the definition of composition, huh? Yes. Yes. Proof. PF. Okay. So now we want to compute the guy, right? So the definition of composition is this, right? So so then I have just a big disjunction on A, I have this, I have that, and conjunction with E of A. And I have to show that it is 1, right? How to do that? Should I really put that things here? That's ugly. Yeah. Okay, let's not compare. That's just too much. The idea is easy, kinda, to say it out loud. So I just substitute this, and then I have one way, and then I use the fact that if you have this and MBA, then you get your age, and then that blah blah, then you can compute 1. So that's just too ugly. I cannot process that. Sorry. But my main point is that you have this as equal 1. What next? The next is the backward direction. So if you have, maybe I have to be honest about the order. So if I have the sub-object of AR, and I have my H subset, let's say chi, then from chi you can define some sub-object. So I have to go from some BS to AR. technically I go actually to from A some R prime to AR. So that is the map M that I want to assign to it. And so if you have a subset, right, how to define a map? You say simply go from, the domain of this to A. But now I can go simply from A to A by changing the extent to which things exist, right? So simply I would say that first I have to define my R prime E prime of A. Existence here is just the usual existence of A here and chi of A, right? I change it by chi to be less existing. And then M is easy, M of A prime. The map maps A to this to itself, so it should be this. But at the same time, I want my A to be here, so therefore E prime of A, right?
Defining left-hand map.
Yeah. Yes. I'm defining two things. One R prime, two M.
E prime of A is something. The right-hand side is an M, A.
I also forgot R prime. Sorry. So R prime also is, say, A1, A2 here is just the same as R, but also I assume that both of them exist. That's just seriously ugly. I'm doing my explanation, right? But out loud. So let me write it down like this. So I'm defining this guy, right? I'm going from some subset chi to some subobject. So proof, or if you like, construction. You start with H subset chi, right? And I want to assign to chi some M chi, which is monique, and goes from some BS to AR, right? So I have to construct this, I have to construct that. So first this guy. So this is simply AR prime. So the set is A itself. Now I have to define R prime. Yes. Yes. I see. But the point is that, let's say that when I write some set here, it doesn't mean that all the things there exist. They exist in different, with different extents.
Some kind of optimized.
No. So you use the same set A, but you change the existing predicate. So I'm pushing that some of the things are less existent. So how? With this R prime.
Some arbitrary.
Yes. Yes. Yeah.
So will this thing be supervised?
Yes.
Okay.
So how to define this R prime? I'm saying that first define E prime of any A here as the existent modified by chi, right? Then this is the first thing. The second is that what is R prime of A1, A2? It is the same as A1 and A2 in R, so equality just with respect to R, but also I want these two guys to exist in the smaller one. Okay? Fair enough? Or not? And the last thing that I have to define is this guy, right? M of chi. So it's a map, and now it is AR prime, and this is AR, so therefore it must be M chi, must be a map from A times A to H with many properties. But the definition simply is this, that if you have chi and say A prime, right? How to define it? The idea is that A goes to itself, right? It is just a subset. Therefore, it must be RAA prime. But at the same time, this A comes from this guy, so it should exist here. Therefore, it is E prime of A. Right? I go there. So what's the point? The point is simply to define the subobject classifier and to show that it is actually subobject classifier. So subobject classifier simply is what? It should be the set of values beside before. So it is simply the H set this.
The subject find this way will be
I have to do many things. The first thing is that this is really a function. Then it is monique. And then it completes the construction. Then I have to show that these two maps that we explained are the converse of each other. And then up to isomorphism, of course, and then we are fine. But of course, we don't do that. So that's just ugly.
Can you just remind what applies?
It means that okay, in this context, for instance. So I guess your concern is that if we go there and come back, right? Then okay. Here it simply means that so the one that you care is this. You start with M, you construct your chi M, right? And from your chi M, you define, say, that M of chi M, which is just ugly. So then let's say that chi and then M prime. And then up to isomorphism simply means that M and M prime are isomorphic, meaning that AR is some object in the category. You have two things. This M prime is A some R prime, right? And this M is some BS. So what I mean is that there exists a map, H set map here, such that this is isomorphism and it commutes. Okay. So back to the busyness of subobject classifier. So subobject classifier should be one object, one morphism from the singleton one, right? So that is the object, because the values are here, of course. And then what is the map? The map, it should go from 1 to this. 1 was that guy. So what is the map here? It should be, we can simply just assign star to something such that it respects the equality, right? So assign just 1, and I have to, because it should respect this, right? So the value should be more than 1, which is just 1. So simply what I'm saying is that this is the set of values, and the chosen value, the T map, that goes from the one in the category, which is this guy, probably to make it less confusing, this, that is just a map that picks 1. And now you have your omega, this is your omega, and this is your T from 1 to omega. And it is the subobject classifier because of the things that I explained in a very rough way. So, meaning, being a subobject classifier simply means that you put the guy here, and your 1 here, your T here, and then it says that for any BS to any AR such that it is monique, there exists a unique map. In our case, it should be chi M. actually yield to be a map between H sets such that this commutes and it is also a pullback, right? And the commutation is that lemma that the composition of these two is exactly one all the time, but it is not enough. So I have to also show that it is pullback, but that is, of course, based on the details is just tedious. So checking all the details. One thing that I have to mention, actually, probably that we are here is that, so what are the maps? So that subobject classifier, if it is true, it simply says that, actually we had it also before, so maybe I can simply say it like this. No, that equivalence that we have, right? If you apply it to this guy, to this H set, H set star 1, it simply says that the subobjects of this are in one-to-one correspondence with what? With H subsets of this, and H subsets are chi from star to H, right? Such that these two conditions, but then you can check that these are just immediate, right? So simply what I'm saying is this: subobjects of 1 are in one-to-one correspondence of the elements in H. Right? They are your values, right? Subsets of 1. Okay, probably that explains that this guy is a topos. So the category of H sets is, that's
-3.
yes, by finite limit, the exponentiation, and the last one, subobject classifier.
Picture here. That's the picture of the T is a subobject classifier.
This one.
Yeah.
Yes.
And so the thing
Yeah.
is,
Yes.
the definition of this thing should be a callback.
Yes. So the definition, yeah. So we claim that this guy is subobject classifier, but we have to prove it. To prove, you have to show that for any monic, there exists unique map.
Okay, I'm just remembering the definition.
That's the definition.
That's the definition.
That's the definition.
And therefore, you say that subobject of
I'm coming back to that equivalence that we have at the top. Yes, the previous one. Which is simply a map from single to star to H. Yes. So what is the map from star to H? It is just one element in H, right?
So the subobjects and H subobjects. So you're in subobjects on the left,
Yes.
and on the right it's H subobject.
Yes. But H subobjects of what? H subobjects, subsets, not subobjects, H subsets of this, right? What does it mean? By definition, it is just a map from the set, right, to H, such that some conditions, right? Yes. So first, what does it mean? It is just a function that picks one element in H. Yes. Therefore, this side is just one truth value. This side is just subobject. Let's read it subset of 1. So it simply says that subsets of 1 are the truth values, which are just the elements of H.
Picking a subset of
Yes.
so more or less just choosing how much some particular, well, there's only one possible thing, one.
Yes.
So choosing how much one is one.
No. You have just one element. To define a subset, you have to pick this star to put it here.
Okay, no,
But to what extent you do it? Okay. That's the point. Okay, the guy is a topos. But actually, that topos is equivalent to a topos that we have seen. And that topos is this. So H set is actually a more logical way to explain the sheaves on H. These two are equivalent.
So we are done for now with proof of this.
Yes.
So can you maybe just give some intuition why this chi you defined as a monic, or how monic maps look in this category in general? Because you define this in this guide, and
Yes.
it should be monic, but
The chi is not monic, M chi is monic. Yes.
yeah, and chi is monic.
Yeah.
Why?
Yes.
Or if there is any easy explanation of how monic maps look.
Yes. So let's write it this way. Okay, let's say that I have just forget about this H subset, etc. Right? That I needed to show that something is a topos. But let's say that I have some map F, right? How to check that this guy is really a monic? Write the H relative version of being a monic. Monic means what? Means that if A goes to B, right? No, in this setting, B goes to A, and what? And C also goes to A. Then B and C should be equal according to the first guy, right? So it is possible to prove that F is monic if and only if you have this. The proof is not that obvious, but very, very messy. Okay. Probably I have to say that epic also has a very good characterization in the same spirit. So it simply says that for any A that exists, then there exists some B that covers it, right? So F is epic if and only if you have this. Again, not that obvious to prove. Yes.
Like, see that these morphisms in H set, some of them come from functions like.
Right.
So can it be easily said like which ones, or another thing is like how do we construct the relation function values?
I will explain.
Okay.
Because I have to say something of that sort later. Okay. So these, no.
Can we have just a basic reminder of what category we're talking about? So originally we have these H sets.
Yes.
And an H set's pair of A and R, where R is a kind of equality.
Kind of equality.
Yes. Evaluating in H, sort of.
Yes. That's the.
We said some good intuitive way to understand that, but I forgot. No, examples were like being eventually equal for sequences and things like that.
Yes. So one example is this. The other is just functions, say, on some topological space, and two functions on, say, different opens. To what extent they are equal? The biggest open where they are equal, right? So that's another one.
And can those both live in the same category?
Both are what? It depends if you have big enough H, probably, but.
Okay. And so you showed some things about this category.
Yeah.
And right, showing that it's topos. And then this business with H subsets is some kind of auxiliary thing you use for the subject.
Yes. To show that subject classifier is a subject classifier.
Oh, I think I mixed up H sets and H subsets. So the H set is the basic thing. The H subset is even more H somehow.
Even more H.
Then I can kind of.
So that okay.
It's just like the picture of a general morphism into H, right? Like because this can be translated into HR, but you can also go back. So it's like quicker and more direct.
Exactly. But since it is more quick, right? So maybe it is better to understand. So the thing is this. So you have one fixed H set, and then let's say that what are H relative kind of subsets of this guy. So you go from A to your value as a map, just the usual real function. And this function says to A, to which extent you pick your A in your subset, right?
You could, maybe this is what you're doing. You could just define an H set in those terms by just, like the equality between A and B is just the maximum of the.
Not really. So I need one set, and then I have to define subsets of that, right? I cannot define sets as subsets.
So let me check can you write the E prime over the subset of A as E conjunction with
Hi, exactly. Yes. So if you define your subset as we did there, right? You have some A R prime, and then E prime, as Pavel is saying, is simply E of A conjunction with chi. So you make it less existent, if you like. So what I'm saying now is that actually we know this category. It is equivalent to H sheaves. Theorem. Yes. That is a theorem that I want to explain a bit of it. But before, last time, if you remember, Pavel mentioned that there is some sort of equivalence, roughly, between Boolean valued models in set theory and forcing. That is the formal statement of that kind of equivalence. This is, yes, Heyting-valued, but you can use H as some Boolean value. It could be any Heyting algebra, any complete Heyting algebra, including some Boolean complete algebra. So then that is your Boolean valued models of set theory, if you like. This is sheaves on something, and therefore something varies over H, if you like, and that is more or less forcing. And these are equivalent, really. These are two different ways of writing down one thing. So how to provide the equivalence between the two categories? So and somehow it's not that obvious, really. One way is easy. So if you want to go from sheaves, let's go this way. From sheaves to H sets, that is not that hard. So remember that on the level of objects, sheaf is just a functor like this, right, with some properties that I don't care for now. And how to assign to this guy one H set. People write gamma F for that H set. So it should be one set, one relation. The set is this. This is just the disjoint union, or if you like, this disjoint union on U's in H, FU. And some R that I will explain later. But first this guy. Simply it says that F is a map on any element U, it assigns a set. Just weave them together as one set. This is just the disjoint union. So the elements are U and the elements on U, right? All of them in one set. So it varies. This is just the screenshot of it, right? So that you have all the changes in one. So more or less this is just the function. It is the graph of the function, if you like, right? You have it just once. And this R is a map. It is a map from what to what? It is the extent of equality. And we saw this guy before, but I can't define it now. Probably also I don't need this. And what is R? Here. R is a map from this guy times itself to H. It reads two things, like U some A inside FU, and V in H and some B inside FV. And what should be the amount of equality between the two? You can think of this u, this a as a function on u, as a continuous function, and this guy has a continuous function on v. And read the u and v. They are in H, I know, but read them as opens of some topological space to have some intuition. So simply, it is just the biggest possible. We had that kind of example, right? The biggest possible open where these two guys are equal. So in terms of the H, it would be just disjunction, the big one, on all C's, such that C, okay, not C, W, such that W is less than U and V. So it's a subset of both of them, such that A restricted to W equals to B. The biggest possible domain where the two guys are equal. Right? Because this leaves over U, it is in f of U. You can restrict it to any f of W because f is a presheaf, it's a functor. And also here, so pick just the biggest possible guy such that they are equal.
Start with the sum over on U.
Yes.
And then,
Which is
six.
I'm defining a function R, right, on this sum. So any element of the sum is just a pair of the U and A on U, and also here V and B on V. So I have to define what I mean by R of these two guys. So I'm saying that it should be the biggest possible domain where they are equal. And of course, you have to check that R is really equality relation. It has the properties that it should. It's not that hard. So that's the first. So what I did is going from objects here, no, objects here to objects here, right? So what about the maps? Sum is just this one union. This sum, right? It is just this one union. So I also have all the names to make everything disjoint. So what about the maps? So we have F, we have G, we have some alpha as some map between them, some natural transformation. And here I have gamma F, gamma G constructed in this form. And I need some gamma alpha, right, to define a function. And it should be a map between H sets, right? And by definition, it means that it goes from, so gamma alpha must be, by definition, from the set of the first guy times the set for the second guy to H, right? And what it should be, again, you have U alpha, no, UR, and VB, but recall that, so note that there's a difference, right? A is in F of U, B is in G of V. And so what, I have to define something in H, and it should be, okay, maybe even better. I can do better. That's easier. This time maybe I have to work with functions directly. So what if I define a function like this, such that it respects equality, right? Then it gives rise to what it should. So how to define the function? That is easy now. You have UA, and you define simply the same U, but you apply your alpha U that goes from FU to GU on A. That lands in GU, right? So too abstract, I know, but this simply says that these two guys varies over H. This alpha says that for any point, you know how to go from F to G. You have a function. So now I weave all of them together, And if I want to go from one to the other, simply I pick one element here, and I know on U how to go from f of u to g of u. I go there, right? So you have to check, and that's the functor. That's good. Problem is that the converse functor is not that easy to construct, really. Yes, that is one of the things that we have to prove actually to show up to isomorphism, to show that they are equivalent, right? That's actually the problem that I have. I will explain. So let's say how to do the converse of the construction that we have. This time you have say the H set AR, and you want to assign to your H set some functor. You have, say, the static image, the graph, and you want to define the variation. So what should be this f, say f AR from H opposite to set? So the definition is what? What should be the real definition? The natural definition should be something of this sort, right? What? So read some u and pick the u part, right? If we think of this sigma, there is some u part here, right? The ones with the extent u. So probably the natural definition here is that pick all the elements in A such that the extent is actually u, right? That's the natural definition. And it is kind of the converse of the one that we had before. That's good. The problem is this, that if it's a functor, then whenever v is less than u, you have to come up with a function from FAR of u, this set, to FAR v. That is kind of the restriction function. You have something on u, and you want to restrict it to v, right? You have to have this function. How to construct it? So naturally, what I'm saying is this. If I have something with the extent of the existence is u, and v is something less than u, of course, there should be some element with that extent, right? At least for functions, you have restriction, right? Probably you have it. The problem is that actually that's not true for any AR. So there are some AR, some H sets, such that they are not that complete. It is possible that you get some elements that exist with some extent, but if you decrease the extent, it doesn't mean that you have some element representing that. So the example is just obvious. That's H set, right? So this guy has the value 1. Any value less than 1, I have nothing here, right? So it's not that complete. So that's some sort of global function that you cannot restrict. So that's that. So if I want to go through this construction, I need to assume something specific about my AR, my H set. And that specific thing is this. So first definition, what is, so we had H subset. Let's call it H singleton of AR. What is a singleton? It's a subset with one element, right? So therefore, it should be is H subset chi from A to H such that it is a singleton. Singleton means that if A is there and B is there, then these two guys are equal, right? And there is one canonical way to construct singletons, right? And that canonical way we go here, that canonical way is just using singletons, really. Right? So if I have some element A in A, then I can define some, let's say, sigma A from A to H as a singleton, right? So define. So this is just the usual construction. You understand that, right? That you go from A to the singleton A, right? So what is the singleton? H singleton. It is sigma A, and it reads B, and it computes RAB, right? That is my singleton. It simply says that for any B, just pick it when it equals to A, kind of the H version of it. And you can check that it is actually singleton. To check that it is a singleton, sigma AB and sigma AC must imply equality between B and C, and RAB, RAC implies equality between B and C, right? So these guys are singleton, H singleton in that sense. So for any A, you have a singleton. But this is not true that all the singletons come from one A and from a unique A. So definition then, H set AR is called complete if the map A to sigma A that we had above is 1-to-1 bijection, is a bijection. What? Bijection between A and the H singletons of A. So what I'm saying is that something is complete if all the singletons in that way are sigma of something, and that something is unique. So singletons are just really elements, right? And we saw that that is not true, really. That is false even for that star one, right? Because why? Because if you have star one, for instance, example, if you have your star one, then one singleton of it is what? Is the map that goes to H from this singleton and picks any U in H. That's a singleton. You can check the definition of the singleton, right? But it does not come from any star. Star represents just one. But if you restrict your one to some U, then you have nothing. The same thing explained with the singleton. So there are two things that I have to say. One, any H set is isomorphic with the complete one. So you can complete your H set. How? So if you start with AR, the one that you have to construct is singletons of R, of A, and the R of it. So let's call whatever, R prime. So here I just have all the sigma, all the singletons, H singletons, and R prime, and define R prime like this, that if you have some sigma and some tau, then R of them is just the existence of some element such that both of them are equal to that, right? So two singletons are equal if there is one element such that it is here and there, right? Therefore, they are equal. This is one way to just explain. And you can see that this guy is H set, and there is a map here. The map simply is A to sigma A, if you like. And so there are some things that we have to prove, but I don't. But first, you have to prove that this is actually now complete. Now that you have all the singletons, it is complete. The second is that this guy is isomorphism. But the second is not that hard. The first is kind of messy. But anyway, point is that any H set is equivalent to a complete one. Up to isomorphism, you can just assume that everything is complete. The second thing is that if we come back here and we change AR to a complete one, right? And if you move me, please, then we can go through this concept. How? So let's say that this guy is complete. And then what? Then you need a map. Define diff. So you have something with the extent u, and you want to construct something with the extent v. How to do it? You go from A to H like this with some sigma. Define your sigma as sigma of any A, simply is E of A, and some fixed V, right? It is easy to see. No, sorry. That's good. No, that was good. Yes. So we can check that this guy is actually a singlet, right? With that property. Since it is complete, there exists some B such that this sigma of A is actually sigma of B of some A, right? Therefore what? You're right. So that's so first define tau to avoid any confusion, and I have to use the rest of the things. So what I want to say is this. That's a theorem kind of that let's say that AR is complete. Then for any A and A in A and any V in H, there is B, unique B even, such that E of B is E of A and V. So what I'm saying is that you pick something, whatever it is, and then you simply restrict the extent of it, and always there is just one element to do that. And then you can pick that one element here, right? You start with U, A with the extent U, restrict it to V, then it should be V, because V is less than U. And then there is just one unique element, pick that. And that is your function. So
It's still the equivalence of sheets and H.
yes, we are.
Still right left.
I don't remember which is which, but yeah. Left, right. Left, right. Okay. So proof of this guy is this. So you need this guy. It should be E of something, whatever. So define tau of any A as E of A and V. Right? I can do that. Then it is easy to see that tau is a singlet. It has that property of singlet. Therefore, there exists a unique B inside A such that it comes from that guy. Which means that sigma BA, so tau B, tau A, say, tau A, let me write this. Tau A, on one side it is this, on the other side it is this, which is just RBA. So you have this equality between B is fixed, but A can be anything, right? Because I define my function like that. So, so I'm really confused what I'm doing. That sounds sort of fishy. So for any A, I have this equality. Therefore, I can have RBB as that. And that is good enough, I guess. But I feel somehow bad because why? Because I guess that tau is defined in a wrong way. I guess no, that should not work. Sorry. Define tau x as sigma A x and v. That should work. Now tau is a singleton. So I guess the bug is here. So let me just check that if it is really a singleton. So to be a singleton means what? Means that you have to respect blah blah, and at the end you have to have sigma A x and v, and sigma A y and v must imply R x y, and that is the case. Simply because this is equality between ax, this is equality between a y, therefore x and y are equal. So yes, now tau is a singleton. Therefore, there is some unique b such that tau is sigma of b, that's fine. Therefore, tau of x is sigma a of x and v, which is sigma b of x. Right? So this is true, this equality is true for any x. And if you have it for any x, then you can prove this. How? Like this. So we have this equality, right? So we put x equals to a once, then we have sigma AA, which is just EA, and V equals to RBA. And once I put this, then it would be RAB and V equals to RBB, which is EB. So this equals to that, therefore EB equals to EA conjunction with V. Okay, so to sum up, what I'm saying is this. If you start with complete ones, so if your AR is complete, then it is possible to come up with some FAR such that at least you can define it as a function on restrictions. You can define it, right?
But this statement of the theorem what you want, because in the statement you just want this something which has this lower e, but you really want to like restrict one symbol to the other one by d.
Yes, but that should be enough, right? Because what? Because here you start with something with the extent u, then you, which is your a, then the theorem says that there exists B such that you have this, and V is less than the extent, which is U. Therefore, the extent of the guy is V. So I have my new guy, right?
There will be many of those.
There will be many of those, yes, which is bad.
Because I think you really want to take the original singleton and just observe, like, to what you are actually proving, that sigma of A, where you pointwise take the meet with V, that this thing is a singleton.
I guess you're right. That is, okay, the problem is that my B is not unique. If the property is this.
Yes.
Yeah, you're right. So the right property is not this. You are so right. So I have to change it with exactly what I have here, such that sigma B of X equals to sigma A of X and B. That B is unique, and I have to use that B here. There is, now I can say, unique B such that. So point is that if you have something complete, then you can define at least the structure of a functor. And that is easy to check that it is actually a real functor. And there I need that uniqueness that Adam mentioned. So the good news is that you can actually prove that it is also sheaf, right? That's also not that hard to explain, but probably, okay, just believe me, because it's just too long. So that would, I guess, explain. So I won't explain the details, but I will explain it in the following. So the idea is you can first also define the functor back, the functor forward, or equivalent, you can do this, which is easier. So you have this functor, you prove that it is full and faithful, and then also surjective on objects, and that is the explanation of surjective on objects. Or you can just expand it to define on the maps. But there is a problem. The problem is that here you are working with a not H set with complete H set, but at the same time, any H set is equivalent or isomorphic to a complete H set. So then technically the best way to prove the theorem is this, that first you change it to, first you define a category of complete H sets that is the following category. This is the category. So you define, say, complete. So we have H sets and, I don't know, complete H sets. The objects are complete H sets, as I defined. The maps are exactly the maps you mentioned. So they are really the functions. So if you have AR, a map from AR to BS is just a map from A to B such that it respects the R. I guess we also need something else to add, probably, that I don't remember. But anyway, so this is a category of H sets. Probably I'm a bit loose here. But the main thing is that the map that we had, the inclusion actually, that maps H sets to CH sets to H sets, that is actually equivalence. So these two categories are actually equivalent. So means that this is just inclusion, right? So there is a map backward, a functor, such that if you compose these two, it is equivalent. So more or less, the only thing that I'm using is just that any map, any H set is equivalent to a complete H set. And therefore, it means that it is, to prove the equivalence, it is just easier to work simply with this. We know how to go from sheaves to H sets, but if we think about that, as again Adam mentioned somehow, we actually land in complete H sets, right? So we have to prove it, but that is not that hard to show that this guy is actually complete, this one that we constructed here. And the map is also in the obvious way we defined it, right? And so that explains that the backward map, or if you want the surjectivity, actually works simply because you land in complete H sets. And then you prove that you have equivalence between the two. And therefore, you have equivalence with the first, right? So that is just the structure of the proof, if you like. Okay. I have to say something else. You don't have time. So probably I have to mention just one small point about these categories. So now we have, okay, one point is this, that the point that I mentioned before. So you may say that we don't need sheaves, right, to prove independence. Because first, H set, sheaves on H is equivalent to H sets. This is more logical, right? Defined in a very better way, kind of. So use that just to prove independence. Problem is that you can capture just sheaves on H, on, say, topological spaces, on complete Heyting algebras. Not any Grothendieck topos is in that way, right? You also have more generalized sheaves, that your site is not just a poset. And this is kind of important even logically. So for instance, the axiom of choice is wrong sometimes here, but it is always true there. So then we need them. One. Two, what do I mean by the axiom of choice is true there? So that's kind of hard to explain. So there are two versions of the axiom of choice here in our story thing. One is following just the idea that whatever we have in set theory, you can write it arrow theoretically, and then it would be your new thing, and then we apply it here, right? So this is what we did all the time. This is one thing. The other is just interpret all, first order language of set theory or whatever, and then the axiom of choice is just a sentence, it should be true. The second is more natural for our independence kind of proofs. The first is kind of weird, but but you can see that the first actually implies the second. That's not important for me now. The only thing that I can do, since I'm not working with the set theoretic language for now, simply is just to explain the arrow theoretic version of the axiom of choice, and we saw it in the first very session, right? The axiom of choice, if you try to write it arrow theoretically, it is something like this, that if you have some surjective function from A to B, and that guy is surjective, then it has some section, meaning that there exists some R or S section from B to A, such that FOS is identity, right? Identity of B. That is kind of using choice. Simply, I'm saying that for any B inside B, F minus B is a subset of A as it is non-empty, because it is the function is surjective, right? So pick one element from any B, and then this is your function S. From any B, you pick some element, and then this equivalence simply means that you pick your element here. Okay?
Can you remind me of the topos and the subjective category?
Exactly. So it is epic. Epic means that the dual of monic. So epic means what? It means that a map is epic if you have two maps. So F is here. If you have GH such that GF equals to GH, no, HF, sorry, then G equals to H. That is epic. And this also has a name. It's called a split epic. A split epic. And the definition is just exactly this. So F from A to B is a split epic when you have a section of it. Right? So then the first version, which is the stronger version of the axiom of choice, people call it external AC, axiom of choice. Yes.
Choose.
Yes. So yeah, I can represent it I can present it in any category, right? So then it would be just any epic splits or is a split epic, right? So that is not true in toposes. For millions of reasons. So first, maybe I have to give you a
You
characterization.
said first and second.
Yes, the second I'm not defining.
This is still the first.
This is the first one. This is the external one. The stronger one.
You're just written, just renamed arrow theoretic as external.
Yes. Kinda. And so what we had some toposes, right? So far, we had Grothendieck toposes and also another representation for some of Grothendieck toposes of sheaves, right? As H sets. So there's a characterization, very beautiful characterization of these guys. So
Slow doing capitals. You just put the
yes, people and yes. So that is the axiom of choice. Surjective implies split. That is the definition of epic split epic. And any epic split is just the external of axiom of choice. One, two, there is some characterization of this guy. So the theorem, not that obvious to prove, is that Grothendieck topos. So let E be a Grothendieck topos, meaning that it is equivalent to sheaves on C and J for some C and J, not just them. Then the following are equivalent. So E satisfies external AC, as I defined here, meaning that in E, any epic splits, if and only if you have this characterization. E is actually equivalent to H sets for some H for Boolean H. For some Boolean H. If and only. External axiom of choice, this one, meaning that any epic splits. So one way means that if you have this axiom of choice in topos, your topos is just H sets for some H, and that H is Boolean, so everything is classical. So axiom of choice implies classicality, one. Two, it actually implies the form of your topos. That's that axiom of choice. There are two of them, remember. So that stronger one, they are in this form. Sheaves on any site. And one specific site is the site when H is just one Heyting algebra, complete Heyting algebra. And then your J means that you have A and some AIs, and these cover A when the disjunction of AIs is A.
Given a particular kind of site,
Yes,
and then this SHH,
exactly,
and
exactly.
you're saying that this actually occurs anyway if your original thing has this.
Yes, if you have a, and vice versa. So if you have some H, which is just a Boolean algebra, complete Boolean algebra, whatever it is, and you construct your H sets, then you have external axiom of choice.
So is there a characterization like this?
No, the Booleanness is a crucial thing.
But if it satisfies the weird non-Boolean choice.
No, because not really, no. Yeah, the point is that axiom, yeah, one of the main points of this thing is that axiom of choice really implies any more or less reasonable wide enough axiom of choice implies Booleanity. So always it is classical. One, two, that whenever I have some Boolean here, as H said, I have axiom of choice in this way. So if whenever I have some Boolean algebra here and construct my H sets, which is good to prove independence, then I always have my axiom of choice, which is good, kind of. So that's one thing. The other thing is that maybe I have to say that Booleanness just alone is not enough to prove the axiom of choice, right? There are some toposes that are Boolean in the sense that subobjects, the Heyting algebra of subobjects, are Boolean, but these guys are not satisfying the axiom of choice. And this is the last thing I promise to say. Huh?
Boolean in some sense, but not in this sense.
Yes, but Boolean in the real sense. So E, a topos, I defined it before, right? E is Boolean if, by definition, for any object A, sub A is a Boolean algebra. It is always a Heyting algebra, but whenever it is Boolean for any object, then I call it a Boolean topos, right? No, for any topos.
But now you're saying it's not the same as being an H set for Boolean H.
No.
Okay.
If your H is a Boolean algebra, then H set is actually a Boolean topos, but not all Boolean toposes are like that. And one obvious example that is not in this form and actually that does not satisfy this is this. So pick G as a group. We have seen this guy before. So the category of all G sets, this is a topos. We saw that. It is simply set to G, right? One, two, it is Boolean. So we can prove that sub-objects, the lattice of sub-objects is just a Boolean algebra. The reason simply is that sub-object means a subset that is invariant under the action of G. And if some subset is invariant under the action of G, then the complement is also invariant under the action of G. So therefore, it is Boolean. But this Boolean does not satisfy the axiom of choice in this way, simply because there are epics that are not split epics. And what is the epic? The epic is this. So one object is G here, G with the action of the G itself on G. And then the star. So that map is epic, simply because in the pre-sheaves, epic means pointwise epic, and pointwise epic means that if you pointwise this guy, right, then you see that you just cover all star. Or you can write down the definition that it is epic, but of course it is not a split epic. It is not a split epic because even there is no morphism in the converse direction. There is no morphism, not just morphisms such that you can compose it with blah blah and then you get identity. There is no morphism here. And the reason is again simple. So the reason is yes, yeah, the last sentence. There is no morphism simply because if there is a morphism, then it means that you pick one element in G such that it is invariant. But under the action of G on G, there is nothing invariant. Everything moves, right? Invariant under all the actions, so not just one. So therefore, there are some Booleans without axiom of choice, and there are some Booleans such that they are not in this form. People actually use this guy in the forcing literature. They call it permutation models. But it is not exactly this simply because it doesn't work really, and the reason is some subtleties that I'm just avoiding for now. That's it. Questions?
The page sets because this always would give us the accepted verbs.
Yes.
Because how it connected with what you said.
As long as, so the real thing is this. Of course, we are interested in Boolean word, right? Because we want to do something classical. As long as we are interested in the Boolean word, if we pick our H set, H should be Boolean. And whenever H is Boolean, it always satisfies the axiom of choice. So I cannot construct something Boolean that refutes the axiom of choice. Then always the axiom of choice is false there. But it doesn't mean anything for us. Yes. So, but yeah, I simply mentioned that you can use this category, right, where the axiom of choice is wrong and it is Boolean, and this is the essence of that permutation models. But the point is that it is not actually the permutation models for some subtleties that I'm not mentioning. So. That was the plan for today, but next time I want to start and explain how to use H sets to prove independence of the continuum hypothesis. And also I use it for arithmetic to just represent the Boolean valued version of the independence of pigeonhole principle from, say, induction for open formulas, for instance, the Paris-Wilkie one. So.
Is this enough to prove independence of axiom of choice?
What do you mean?
I mean, we have G set, one suppose where G doesn't, the epic doesn't split.
Yes.
And we have this example with Boolean H sets and the X2.
Yes.
So will we prove independence of?
Not really. So that's the thing that I had to explain. So what is really proving independence, right? Proving independence means that in any way that you want, interpret your set theory, it can be anything, such that everything really in ZF, say, is true, and C is false, right? This is kind of the idea behind axiom of choice. We don't know how to interpret set theory inside toposes. That's not really fair because in some sense set toposes are set-like. So probably it is possible to interpret them. At least I didn't mention that. But there is a subtlety to interpret set theory. And the subtlety is about induction, the axiom of induction F in ZF. And if you want to do that, then something bad happens. And if you do it on this topos, then you see that you cannot use all the objects in the topos as your sets. They have to be well founded somehow. And if you use them, then all of them respects the action of G, so you cannot see the change under G. Therefore, it's just useless. Except that you have atoms in the language, and then you can use it. And this is just the real permutation model that people use, that set theory with ZF plus some atoms, then you cannot prove the choice.
I mean, you have to do some.
Yes.
Finish by 4 o'clock.
That's true. So bye-bye. So bye-bye.